Hey everybody, and welcome to our first video for food chemistry, video by me at least, which is all about significant figures. So significant figures are very, very important in the chemistry lab, but when you sit down and really think about significant figures and what they mean, significant figures are also super important in life, but especially in the kitchen, because when we measure, we have to deal with significant figures because there's only so much. We can only be so certain about a particular measurement based on that particular measuring device. And we're going to talk more about what this means as we progress through this video so you get a little bit of an introduction to what a significant figure is. So I saw this online and I thought it was so relevant because it made a lot of sense and it really puts a significant figure and what that means into perspective. So here's some picture of some Tyrannosaurus Rex, skeleton that's at a museum. And somebody said, how old is this skeleton? Right? So the visitor says, how old is this? And the person says, well, this is 70,000,006 years old. And when you think about it, you're like 70,000,006, like how that's oddly precise considering how old this skeleton is. So the visitor comes back and says, how can you be so precise? 6 years, I could see 70 million, but where'd you get that extra 6 from? And the guide says, well, 6 years ago when I started working here, they told me it was 70 million years old. So it must be 70,000,006 years now. But that first 70 million, when it was first told to the person, so they went to the museum, they said they're learning about everything. Oh, this Tyrannosaurus Rex is 70 million years old. Okay, well, how exact was that measurement? Do we know that this thing died exactly 70 million years ago? Probably not. It's just a rough estimation. So for that tour guide to say it's 70,000,006 years old, you can't be that precise because that initial estimation wasn't that precise to begin with. And that's where significant figures come in, is how exact can I be based on the exactness of the original data that I'm working with. So for example, you're going to see a whole bunch of these measuring devices, and we're going to use a lot of these in class. So at the top, you're going to see a ruler, there's a stopwatch, there's measuring cups, there's the scale, right? Graduated cylinders and pipettes. There is some uncertainty when we are measuring with those particular devices. So if I'm trying to measure the length of a Cheez-It, which you're going to do eventually, we can only be so exact in that measurement because the ruler is only reading so many digits, right? The ruler can't tell us that a Cheez-It is 3.7654321 centimeters because it doesn't read that many decimal places. If you're using a scale to bake with and you put flour on a scale at home and that scale reads 200 grams, yes, we know that it's 200 grams, but I don't know if that flour is 200.27351 grams because that scale is not reading those additional measurements to me. So there's some uncertainty when we are measuring, not only in the chemistry lab, but also in the kitchen. You might have made a recipe once and it came out great. And then you made that recipe again and you're like, oh my God, this came out like garbage this time. Why did that happen? I did the exact same procedure. It could be because those measuring devices, there's some uncertainty with those, and that could skew a whole recipe quite a lot. And that's true more so for baking than cooking. Baking is more of an exact science, whereas cooking, not so much. You can kind of add more or less spices if you want to, but for baking, you have to be pretty accurate on those measurements. So let's say that I'm measuring some peanut butter on a scale. So I try not to eat too much peanut butter because it is very high in calories and fat. So I have to try to limit how much I eat because I can just scoop it right out, right? It's so good. So let's say I'm measuring peanut butter on a scale and that reads 36 grams. That particular measurement has only 2 significant figures, and that's because that's what that scale is telling me. The scale is telling me that it is 3, 6. That is 2 values. The scale is not telling me that it's 36.0000. We don't know what those digits are beyond that decimal point because the scale is not reading that to me. So I can't be that precise. So 36 grams of peanut butter on a scale has 2 significant figures. What about if for a recipe, let's say I'm making muffins and it calls for 1 cup of oil, and I measure 1 cup of oil in a relatively large measuring cup that measures, maybe 2 cups, let's say. That 1 cup has 1 significant figure. And that's because when you add oil to a measuring cup, it might not be exactly 1.000000 cups. That measuring device, that measuring cup is only reading 1 cup, 1.5 cups, 1.5 cups. So I can't be that exact on a measuring device that's not that exact to begin with. So that 1 cup of oil has 1 significant figure. What if you're looking for a range hood for your kitchen? So you go on Lowe's.com and you see there's all these range hoods. And I was clicking around on the website for a little bit, and I just clicked on 36 inches, right? And this particular range hood came up, and it says that this range hood is 35.87 inches long. That particular measurement has 4 significant figures. Look how exact that number is. This particular measurement comes out to 2 places after the decimal. This is a lot more exact than, let's say, these are 36-inch range hoods. So that 35.87 has 4 significant figures. Every single one of those numbers means something very important in that measurement. If you're trying to fit something for a particular space, you want to be as exact as possible. So you're going to make sure that you follow all those significant figures. A couple more examples. Let's say you have 3 eggs in a recipe, right? You need 3 eggs. Is there any uncertainty in those 3 eggs, right? You grab 3. 1, 2, 3. That particular value has an infinite number of significant figures. And this is where we start to get a little iffy. And that's because you can literally count 3. I need 1, 2, 3 eggs. Because you only have 3 and you can hold 3 in your hands, that's an infinite number of significant figures. I didn't measure that. I counted that. So because I can count that and because that number is exact, that has an infinite number of significant figures. If I say that there are 24 students in the class, that has an infinite number of significant figures because I can count that value. There's no uncertainty in that. I don't have people's limbs in some drawer somewhere. You might think so, but I don't. So that is an exact number. And the last example, 25 minutes in the oven, right? 25 has 2 significant figures. You might put that in, right? You put the stuff in, the cookies in, whatever it is you're making, and it's in a little bit longer than that because you don't even start the timer to begin with, right? So you put them in, they're in there for a couple seconds, then you set the timer. Then the timer rings, you're sitting in the other room, then you go back, right? It's about 25 minutes. It's an approximation. So that particular value, 25, has 2 significant figures. There's some uncertainty in that number because if I use a stopwatch and count exactly 25 minutes, that's going to look different from the time that you put something in the oven. And sometimes when you're baking, those extra couple of seconds or minutes makes a big difference. So let's go ahead and talk about really quickly, how do I count the number of significant figures in measurements? The reason why you haven't worked with this before in your math classes or your science classes is because you very rarely deal with measurements. When we're in chemistry, and especially in cooking, there's some uncertainty to our measurements, and we have to take that into consideration when we are doing calculations with these measurements that might not be that precise to begin with. So all numbers other than 0 are what we consider significant. I think this rule is pretty straightforward. So for example, if I have 1.5 cups of rice, that has 2 significant figures. If I'm making dinner and if I measure 1.5 cups, I have the 1 cup, I have the half cup, I might go a little bit above the half. Let's say I'm a little extra hungry that day. It's about 1.5 cups, right? There's some uncertainty in that measurement. So that has 2 significant figures. 7 minutes in the air fryer, that has 1 significant figure. It's about 7 minutes in the air fryer. If I measure out 145 grams of flour on the scale, those scales you use at home in the kitchen are not as precise as the ones that we use in class. And you'll notice that because there's no decimal places next to that number. So as a result, this particular measurement has 3 significant figures. Let's say I measured this on one of the more intense scales in the room that measures out to 3 places after the decimal. And if I have 145.000, that has 6 significant figures. So we're starting to see the differences in precision just based on the values that are represented. Any 0 that is trapped or sandwiched between 2 other numbers is always considered significant. So for example, if I measure out 101 grams of blueberries to make muffins, because that 0 is sandwiched or trapped in between those 2 ones, that makes that 0 considered significant. If I have 8.005 seconds. Now, this is a weird measurement for cooking because, like, why would you measure that number? I tried very hard to come up with different measurements for this. So some of them are not directly related to cooking, but you get the idea. If I have that 8 and that 5 and 2 zeros in the middle, those zeros are considered significant because they are trapped. So that has a total of 4 significant figures. And lastly, let's say I measure a teaspoon of vanilla, and a teaspoon of vanilla, we'll just pretend, has a volume of 3.02 milliliters. That particular measurement has 3 significant figures, again, because that 0 is sandwiched or trapped. Rule number 3 says zeros that are in front of a measurement are never significant. So if I start a number or a measurement rather, if I have a measurement that starts with a 0, that 0 is never significant. So some examples, let's say I'm making muffins again and I need 1/4 cup of brown sugar. So I have 0.25. Because that 0 is in the front, that 0 is considered insignificant. It does not count in the precision of that particular measurement. So normally what I like to do when I'm doing this on paper, whenever I see a 0 in the front of a measurement, I tend to put my pencil down and I cross out those zeros in the front until I get to a number that's not a 0, because everything after that will be considered significant. So 0.25 cups will have 2 significant figures. 0.5 hours in the oven. So if you put something in the oven for a half an hour, again, I'm going to put my pen down and I'm going to cross these zeros off in the front. That 0 is considered insignificant. It is what we call a placeholder. So that particular measurement has 1 significant figure. Or if I have 0.00100 liters of milk, again, I have zeros in the front of my measurement. I'm going to put my pen down and I'm going to cross off all those zeros in the front till I get the first number that's not a 0. In this case, it's a 1. And everything after it will be considered significant. So in this particular measurement, this has 1, 2, 3 significant figures. Rule number 4, so this kind of deals back with what we were just talking about with that last one. Zeros at the end of a measurement are only significant if there is a number that's not 0 in front of it. So some examples. If I have 2.50 cups of sugar, so here I have a 0, but I have a decimal point. And because my first number is a 2, it's not a 0 number, everything after it is considered significant. So 2.50 cups of sugar has 3 significant figures. If I have 100 grams of almonds, here, notice how there is no decimal point. in this case. This particular number is not that exact. This is like the 700 million example. That is an approximation. So if I say, no, you need 100 grams of almonds for your salad, right? That's an approximation. You could go a little bit above that. You could go a little bit below that. It's just about 100. So this only has one significant figure. What if I did something like 100.0 or 100 decimal point? Adding that decimal point at the end makes a difference. That means we have exactly 100 grams. So this particular value, because of that decimal point, would have 3 significant figures. I'll just put SF there for that. And if I have 0.250 quarts of milk, again, I have this 0 in the front. Anytime you have a 0 in the front, I put my pen down and I cross out those zeros because they're never significant. However, my number that comes next is a 2, and therefore everything after it is considered significant. So this particular measurement has 3 significant figures. Last rule, anytime we have a counting number or anytime we have a conversion factor, all of those have an infinite number of significant figures. So for example, 1 cook in the kitchen, right? 1 cook, I'm not going to have, there's no uncertainty in that because I can't have a quarter of a cook somewhere. If there's 1 cook and I can count that 1 cook, that has infinite number of significant figures. It's exactly 1. If I made 40 meatballs and I counted those 40 meatballs for a soup, that has an infinite number of significant figures because I made exactly 40 grits. They're different sizes. So the mass would have a different number of significant figures. But if I counted 40, that has an infinite number of significant figures. And also the fact that there are 12 inches in 1 foot, that is a fact. We know that. There is no uncertainty in that. So that also has an infinite number of significant figures. Remember, you've never seen any of this before, and that's because you've probably not worked with measurements all too much. Now that we are starting to introduce measurements in chemistry, we have to consider what's the uncertainty in these measurements, and that's what we're going to focus on with significant figures. So let's do some really quick mixed practice. Let's say I have 15 minutes in the oven. How many sig figs? Should be 2 significant figures. What about if I have a dozen cookies, right? A dozen cookies. You count them, there's 12. How many significant figures? Should be infinite number of significant figures. Let's say I have 1.5 teaspoons of vanilla, 1.5. If we're talking about estimations here, how many significant figures are in that measurement? There should be 2 significant figures. 1.5 teaspoons is very different from counting 1 dozen. I can count 12. There's exactly 12, but there's some uncertainty in 1.5 teaspoons if I'm using a measuring device. 0.890 grams of cream of tartar. How many significant figures? Should be 3 significant figures. That 0 in the front does not count, but that 1 at the end does in this case. 1,050 milliliters of water. How many sig figs? Should be 3. That's because that 0 in between the 1 and the 5 is considered significant. The 1 at the end is not because there is not a decimal place there. Last example, if I have 10.00 milliliters of soda for the experiment, how many significant figures? There should be 4 with that one. There is a decimal point there. That 1 is significant and therefore everything after it. If you have any questions, of course, you can ask me during the next class. We are going to get a lot of practice with this throughout not just the next few days, but throughout the duration of the course. So otherwise, I will see you in the next video and I will see you in class. Bye.